Okay, here we go. A little bit of talk about fractions and rational numbers and what they are, what the difference is between those. The way that we're going to define a fraction is that's any number over any number. I'll contrast that with rational numbers in just a second. A rational number, very similar to a fraction, a rational number is an integer over an integer. So, for example, a rational number is something like 2/3 or -4/7, something like that, where we have an integer over an integer. I mentioned that a fraction is any number over any number, and you might be thinking, well, what would be a number that's not irrational? Well, an irrational number, if any of you took Algebra 2, you might have encountered these, but something like square root of 2 over 2. That would be an irrational number. Square root of 2 is a non-terminating, non-repeating decimal, so it's called an irrational number. And so while square root of 2 over 2 would not be a rational number, it is a fraction, because a fraction can be any number over any number. The distinction between those isn't going to be something I'm going to quiz you on or put on an exam. I just want you to be aware that fraction is sort of a wider term than rational number. Rational number is a little more narrow, integer divided by integer, and those are going to be the focus for us, is rational numbers. One of those things where I said you probably are familiar with this, but just as a reminder, when we have a fraction, the top number is called the numerator, and the bottom number is called the denominator. So that terminology that you're probably familiar with, but maybe it's rusty, maybe it's been a while, we're gonna use those terms. So the numerator's on top, the denominator's on the bottom. We're going to talk about some different models that will allow us to draw pictures of fractions. And the models that we're going to be interested in are called the length model, the area model, and the discrete model. Our book uses the term discrete model. I've also seen this referred to as the set model in other places. So it's also known as the set model. If you see discrete model or set model, it means the same thing. And that's the third of the different types of models that we'll see for displaying fractions. Let's start with the length model. Basically, it's exactly what you would think. It's like a ruler or a number line. If we wanted to show 2/3 using the length model, we just set up basically a number line where we go, say, from 0 to 1. And then I could sort of section this off. That's where 1/3 would be. That's where 2/3 would be. And if I want to indicate 2/3 on my length model, I'll just put a dot there. And so that's what 2/3 looks like in a length model. Basically, it's a number line, or you can think of it as a ruler if you want to. That works too. The area model. And this is one that we'll spend most of our time with, is the area model. With the area model, we essentially draw a picture of what 1 would look like, and then we need to chop it up so that we can indicate 2/3. And the way that we can do that is we'll go ahead and cut it into thirds, and then shade 2 of those 3 pieces. And if I shade these 2 pieces over here, I've drawn a picture of 2/3. I've shaded 2/3 of the area of that circle. So that's why that's a picture of 2/3, and that's the area model. Doesn't always have to be a circle if you want to, and you'll see examples of this later on today. You could cut a rectangle into thirds, and you could shade 2/3. So it doesn't have to be a circle, it could be a rectangle, but we'll draw a picture of 1, and then we'll cut it up and shade so that we can see the fraction we're trying to show. As I talk about these, let me know if you have any questions about any of it. Discrete model is a little different than those. With the discrete model, we're going to just go ahead and set up individual items that represent our set, if you will. Because remember, this can be known as the set model. And then if we want to show 2/3 of that, well, I have 3, so I'll just circle 2 of them, and that's a picture of 2/3. If we were making a set model and we wanted to show 2/3, we wouldn't put 4 X's in there because that would be really hard to show 2/3 of. We'd go ahead and make it something that's easy to show 2/3 of. Maybe it's 3 and we circle 2 of them. Maybe it's 6 and we circle 4 of them, something like that. But so when we use the set model, we go ahead and use it in a way that's convenient for us. Let me know if you have any questions on any of those before I give you a chance to practice. All right. I'm not going to set up a poll for this, but I do want you to just try showing 3/4 using the length model, the area model, and the discrete model. And I'm just going to give you a couple of minutes to try to draw pictures of those, the length model, the area model, and the discrete model. And then once you've had a chance to do that, we'll go through it together, and you can let me know if you have questions about any of it. But I'll just kind of pause here for a minute or two and give you a chance to draw those. Okay, if you're still drawing, that's okay. Just sort of take a look back and see where we are and let me know if you have any questions. We want to show 3/4, and using the length model then, I'm going to set up my number line. I'm going to go from 0 to 1. I'll put a half in here, and I'll put 1/4, and then this is where 3/4 would go. And then if I want to indicate 3/4, I'm just going to put a dot right there, and that's 3/4 using the length model. One thing I want you to notice is on this number line, that's 1, 2, 3/4 of the way to 1. That's where 3/4 is. That's how we see 3/4 on the length model. If I was going to walk that, I'd be 3/4 of the way to 1 when I got to that red dot. For the area model, you could certainly do this with the rectangle. I'm going to do it with a circle. And because it's 3/4, I want to cut this into fourths. That's not so bad. And then I want to shade 3 of them. It doesn't matter which 3 you shade. You can shade any 3 you want to show 3/4. It could be any of the 3 pieces. Just make sure you shade 3 of the 4. And then with discrete model, if I want to indicate 3/4, I'm going to have 4 things, and I'm going to highlight 3 of them. It doesn't matter which 3 you highlight. They'll probably be next to each other. That's a lot easier to circle and identify. But that's 3/4. So there's 3/4 using the length model, the area model, and the discrete model. Let me know if you have any questions on those before we look at some questions that are more like problems to solve. Okay. Place 5, 6 on this number line. So we want to put 5, 6 on there, and we don't want to just totally ballpark it. We don't have to get a ruler out and measure and be extremely precise. But the way that we're going to go about this is first we'll put 1 on there. Okay, well, still 5, 6 is pretty hard. I don't know if I can cut this piece over here into 6 very easily. So instead of that, I think I'll cut it into thirds. And then I'll have 1/3 here, and I'll have 2/3 here. And that's helpful, but it's still not ideal. But then what I can do is, well, if that's where 1/3 is, then halfway to that would be where 1/6 is. And now I can see how big 1/6 is. And this is a little bit of a reminder of working with fractions and getting equivalent fractions. Where I have that 1/3, if I multiply the top and bottom by the same amount, I get an equivalent fraction. And this is probably review. It's also something we'll talk more about as we keep going, but 1/3 is the same as 2/6. And then, okay. And then if I get to here, I guess if that's 1/6, 2/6, this would be 3/6. 2/3, that'd be the same as 4/6. And then here is where 5/6 would go. And if I want to indicate 5/6 on that number line, that's where it would be. And that's a length model type of questions. Can you identify where 5/6 would be? And you don't want to just kind of totally ballpark it. It's a beautiful way to review fractions and equivalent fractions. The idea that 1/3 and 2/6 are the same. The idea that 2/3 and 4/6 are the same as each other. And then when you're counting over, you're just kind of going, well, all right, that's 1/6, 2/6, 3/6, 4/6, 5/6. And that's where 5/6 will go. Let me know if you have any questions on that before I have you try one. All right, my feeling is we're doing pretty well. You'll have to tell me if that feeling is wrong. So now what I want you to do is determine the value of X on that number line. I'll make a poll for this one and let you try it. You don't have to be in a hurry here. You kind of want to take your time and make sure you're logical about your approach. That's kind of the main thing, is make sure you have a reason for your answer. Make sure you had a process for coming up with it. Because we don't want to just guess. That we can do better than that. We'll go another, let's go another 20 seconds, and then we'll talk about this one together. All right, let's see how we did here. Okay, not unanimous, but strong agreement. That's good. That's very good. I'll go ahead and let you know that 5/8 is the correct answer here. Somebody who had 5/8 as an answer, what was the, you don't have to tell me the whole process, but what was the first thing you did? What was the first thing you found? Counted up to the middle. Okay, Stephen, I like the specificity of that. That's really good. Perfect, Kate. That's terrific. Will, I'm not exactly sure what you're going for there, but you can let us know if we do something similar when we find it. And Lee got the same thing as Kate and Stephen. That's terrific. And so if I know that here is 1/4, then halfway to that must be 1/8. What I was trying to find here is what x is. And now what I've done, just with this one thing of finding that that's 1/8, is that means that one step along this number line here is 1/8. And so if I go here, that's 2/8. And if I go here, that's 3/8. And if I go here, I'm not going to worry about reducing this. I'm just going to call it 4/8. And then if I go here, I must be at 5/8. Each step along this is 1/8. So when I do 5 steps, I must be at 5/8. And let us know if you have any questions on how we got there, but that is a solid approach. There's certainly other ways to do it, but I think that's the most common, and it's very understandable. Okay. Locate 5/6 on the number line. Now, I don't think this is an easy question at all, but I am going to just sort of take a step back and give you a minute to try it. I'm not going to do a poll or anything here. I'm just going to let you try to figure out where 5/6 would be. And then here in a minute or two or three, we'll do it together. This is one that not everybody, it's possible that not everybody does this one the same way. And it's kind of challenging, but I think when we talk through it, it'll make sense. And you can absolutely let me know if it doesn't. I'll go ahead and start talking. And if you're still working on it, that's fine. You stop me or ask questions or whatever you want to do there. One way to approach this is to say, well, it's 1, 2, 3, 4, 5, 6, 7, 8 steps got me to 2/3. So if I go half that far and I just go 4 steps, then that's going to put me at 1/3 because that's half of 2/3. So halfway there is going to be 1/3. 4 steps, 1, 2, 3, 4. So that's 1/3. Well, that's helpful. And some of you might have just looked at this and said, well, if I go halfway, that's 1/3. Great, fine, nothing wrong with that. And then figure out that it's 4 steps after you found the 1/3. That's fine. Of course, what I'm after here is 5/6. So I kind of want to cut this thing into 6. Well, if that's 1/3, if I go half of that, that's where 1/6 would be. And so now what I can see when I look at my picture here is that 2 steps is 1/6. Well, I want to go 5/6. So I'm just going to do 2 steps 5 times. So there's 1, 2, 3, 4, 5. And then this is where 5/6 has to be. And if you wanted to count that different than I did, if you wanted to go, for example, okay, 1/6, 2/6, 3/6, 4/6, 5/6, then that's fine too. But basically, this is very similar to what we did in the last one. We broke this down to figure out how much do I need for 1/8. Then I'll count over here and see where I'm at, and I'm at 5, or how much is one space? 1/8. I'll go to see where I'm at, and it's 5/8. In this one, how much is one step? Well, I don't really care about one step. but I do care about 1/6 because once I have 1/6, I can get to 5/6. Let me know if you have any questions on that using the length model. All right, terrific. Let's talk a little bit about the area model. If that rectangle equals 1, show 4/5. And the way we're going to go about that is we want to cut this into 5 equal pieces and shade 4 of them. And I think with that rectangle, it's going to be pretty hard to cut those horizontally. You could if you wanted to, but I'm going to cut them vertically. They don't have to be perfect, but 1, 2, 3, 4. Yeah, it's a little too far off. There, that's not bad. Doesn't have to be perfect, but we cut it into 5 equal pieces, and then I'm going to shade 4 of them, and that's what 4/5 looks like using the area model. And you let me know if you have any questions on that. Probably not. The area model usually goes really well, and that's good because that's the one we'll spend most of our time with. Discrete model. This one is a little bit harder to accept right away, but the key here is to use the picture along with the fractions that you have, and I'm going to explain that so you won't have to guess. So if we want to show 2/3 in this discrete model, so this whole thing over here is equal to 1, and I want to show 2/3. What I want to do then is I want to look for a place where it's easy to identify thirds. And if I look at these rows, I have 3 of them. So if I want to identify 2/3, then I just need to circle 2 of those 3 rows. And that's how I've identified 2/3. Don't overthink these. Up next, I want to identify 5/6. Well, if I want to identify 5/6, now I want to look and see if there's an easy way to identify 6th. And if I look at these columns, I have 6 of them. So if I want to identify 5/6, then I just need to section off 5 of those 6 columns. And that's how I can identify 5/6. So 2/3, we looked at the rows because there's 3 of them. 5/6, we looked at the columns because there were 6 of them. Let me know if you have any questions on those. Okay. I'll tell you that these two are going to be our primary focus. You will see something like 4/9, I think, in a homework assignment, but it's not going to be a major focus for us. But I do want you to understand how this could be done. If we want to show 4/9, 4/9 is a little bit harder to show here because, okay, I was looking for thirds, I had those in the rows. I was looking for 6s, I had those in the column. How do I have 9s? Well, to get 9s, what I'll do is I'll make little groups of 2. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And now I want to identify 4/9. So I just kind of pick 4 of these to identify, and there's 4/9. Similar idea, we're circling 4/9 of what's in there, but a little bit more strange because we couldn't just use the rows and columns. Using the rows and columns will be primary for us, but I want you to be aware of how this would work. Let me know if you have any questions on any of those 3, 2/3, 5/6, or 4/9. Okay. So if that equals 1, I want you to show 3/4. And I won't do a poll. I'll just kind of give you a second to jot that one down and identify 3/4. If you need more time, you just tell me, or you can finish it up and then we can look at it together. But if I want to show 3/4 here, there's actually two very good ways to do this. If I look at the rows, I have 4 of them. So I could circle 3 of those rows, and that's 3/4. Of course, you may have done this differently. You may have said, well, wait a minute. What if I want to do my 3/4 by looking at the columns? Because there happens to be 4 columns in this particular picture. And so I could circle 3 of those columns, and that would be 3/4. Perfectly fine. Or you might say, well, I did 3/4 with the columns, but I circled these 3. That's okay too. As long as you've identified 3/4 of the picture, there's more than one way to have a correct answer here. Let me know if you have any questions about that one. Okay, I'm gonna increase the degree of difficulty a little bit here. Given that picture is equal to 4/3, this time your job is to show 1. So far, we've always had our initial picture be 1, and we were looking for a piece of it. This time, our initial picture is 4/3, but we want to show what is 1. If that picture's 4/3, what would 1 be? Think about that for a minute. Try it, and we'll do it together in just a minute. One thing I'll tell you is when we had a picture that was equal to 1 and we were trying to show a fraction, the denominator was really important to us. If I wanted to show 2/3, I had to figure out where those thirds were and then go identify 2 of them. This way, when we're trying to show 1 and we already have a fraction that's not equal to 1, it's the numerator that's really important to us for a starting point. What is it that I have 4 of? Is kind of where we start this one. And what we're doing here is we're trying to show 1. Well, in terms of thirds, 1 would be 3/3. So if this is 4/3, then that means that each one of these columns must be 1/3. That's how I get 4/3 here. And if I want to show 1, which is 3/3, then I just need to pick 3 of those columns that'll be 3/3, and then that's what 1 looks like. So if that whole thing is 4/3, then what I've got circled here in purple is what 1 would be. Hopefully that makes sense. If it doesn't, you feel free to ask whatever's on your mind. I think these models are probably new for most of you. They tend to go great for students. Students kind of enjoy these in addition to doing well with them, but I want to encourage you to ask questions if you have them. Okay. A little bit of problem solving. And this is the kind of thing that could definitely be done with students. 8 inches is what part of a foot? And in some ways, that what part is almost like saying what fraction of a foot. And with the length model, you could say, well, we'll start out with our length model. And since we're talking about a foot, we'll go all the way over here to 12. And if we're going to have 8 inches, now I want to section this thing off. And just so I'm a little bit more accurate, I'll probably put a 6 and then maybe a 3 and a 9. And heck, I'll go ahead and do the rest of these and have 1, 2. And we've got them all in there. And then, okay, well, this is where 8 would be. And so if I'm doing 8 inches is what part of a foot, and I'm using the length model, that's where 8 inches is. At a quick glance, a student can see that it's more than half. And then, well, I'm going 8 out of the entire thing, which is 12. So I could say that it's 8/12 of a foot. If you're not reducing fractions yet, then that answer's fine and it's okay. If you are teaching them to reduce fractions, then we want to divide top and bottom by, we could do it, divide top, those are both even numbers. So we could divide them both by 2 and call it 4/6. And Hey, I still have even numbers, so I could divide by 2 again. Say that 8 inches is 2/3 of a foot. Or you could leave it 8/12. I don't see any harm in that if you're just sort of working on problem solving and it's an introduction to fractions. In some ways, this is a beautiful way to show how to get 8/12 and then how to reduce it. It's a really nice problem that way. The length model is really just a visual representation here of, you can kind of see that if I'm going from here all the way to here, that this spot right here is 2/3 of the way. One of the things I want to have you tell me is, given a problem like this one, there's a diagram. This is an area model. What fraction of that diagram is shaded? And I'm not trying to trick you here with a trick question. This part down here is shaded, and so is this. It's not nothing like that. It's what part is shaded. Don't overthink it. How much of that is shaded? All right, good. Laura, Katrina, Kate, you're exactly right. 1/4 of that diagram is shaded. Essentially, what we're saying here is this part that I have shaded, it would take 4 of those to make the whole thing. It would take 4 of this to be the whole picture. Keep that philosophy in mind when we look at this next one. What fraction of the diagram is shaded? I think this one's a little tougher, but keep that philosophy from the last one in mind when you answer this one. And it's okay if not everybody has the same thing here. Okay, Kate's got 1/8, Sean's got 1/8, Laura's got 1/8, Katrina's got 1/8. Very good. I'm thrilled with that. I will tell you the most common mistake that students make here is they go, well, there's 1, 2, 3, 4, 5 pieces, so 1/5 is shaded. That is an extremely common mistake here to make. If you were thinking 1/5, you probably weren't alone. Somebody else was probably think that too, because there's 5 pieces. So 1 out of 5 is shaded, so it's 1/5. But that only works if they're all the same size. Here, when we want to know what fraction of the diagram is shaded, essentially what we're saying is, how many of this would it take to make the whole picture? Well, there's 1. It would take another one down here, would be a second one. 2 more down here, 2 more down here, 2 more up here. Sure enough, that's 1/8 of the whole picture, not 1/5. Be careful with that. When we get to that page that I like to do before an exam, and I say this exam will include a trick question. No, it won't. That's not a trick question, because we are going to talk about it and you'll see it again for sure. Remember, it's how much of this would it take to make the whole picture, not just how many pieces are. It works here. How many pieces are there when they're all the same size? But when they're not all the same size, really think about how many of these would it take to make the whole picture. That's the fraction that we've shaded. If that doesn't make sense, you please feel free to ask about it. Outstanding. Very good. Okay. I think these can be a little bit difficult. It's kind of an area question. It's also kind of a length model question. But if that diagram below is 1.5, show 1. Some of you who are extremely visual will thrive with these. For me, I can't really do it that well visually, but some of you I bet can. Some of you who are really visual might look at this and say, well, 1.5, let's see. We haven't talked about mixed numbers in this class very much yet, but 1.5, you may remember, we could rewrite as an improper fraction. And we're going to revisit this again later on, but for right now, that's, let's see, 1.5, that would be 1 plus a half. 1 we could write as 2 halves plus 1/2. So if I were to write 1.5 as an improper fraction, it would be 3 halves. These two things are the same as each other. If that doesn't make sense, you can ask about it. It's totally fine. So this is 3 halves. So this diagram that I have here, that's 3 halves. Okay, 1.5, 3/2. Some of you might look at it and go, well, okay, then if I chop this into thirds, then right here, that's a half, and right here, that's a half, and right here, that's a half. Since 1 that I'm trying to show is 2/2, I just need these two put together, and so 1 is going to be right there. I think that's kind of hard. I wouldn't do it that way. So if you wouldn't do it that way and you're thinking there's got to be a different way because I didn't see that, it's okay. Just breathe for a minute and we'll talk about it. Some of you who are really visual might see it just like that, and that's perfectly fine. Others who are a little more, I don't know, don't just sort of see things right away. I'd be in your camp. Um, might say, okay, then. So you're telling me that this is 3/2. And I look at this and it's 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. So 3/2 of 1, 3/2 of 1 is 9 blocks. And I'm actually going to set up an equation here for this then. And I'm going to say, all right, so let's see then. 3/2 of is multiply. 1 is the thing I'm trying to find. So I'm going to call that x, and that's 9 blocks. And now I have this equation I can solve. What am I going to do to get this 3/2 to go away? What do I need to do on the left-hand side to make that 3/2 go away? And if you don't remember, that's okay. We haven't done a ton of solving equations in a while. If it's a little rusty or you don't remember, it's all right. We're definitely going to talk about it. But how to get that x by itself. If 3/2 of 1 is 9 blocks, multiply both sides by 2. I like that, Laura. We could do that. Anything that might be do to get this done in one step? But Laura's suggestion is excellent. We could absolutely multiply both sides by 2. We just have another step to go afterwards. If you don't remember this, that's okay. We're going to treat it as though it's brand new. If you do happen to remember, I wanted to give you a chance to say it. Okay, multiply by 2/3, Stephen has in there. The idea is if we have a fraction that we're trying to get rid of, we can multiply by the reciprocal of that fraction, which is flip it upside down. If we multiply by 2/3, then these 2's cancel and the 3's cancel, leaving us just the x. If I multiply by 2/3 on the left, I have to multiply by 2/3 on the right. And then on the right-hand side, we've got to multiply 9 times 2/3. I can make that into a fraction as 9/1. And we're going to talk more about multiplying fractions later, I promise you. And then on the top here, let's see, we've got 9 times 2 is 18. On the bottom, we have 1 times 3 is 3. And then we can divide that and get 6. I'm going to talk back through this whole thing so you see it again. What we just found out is if this entire thing of 9 blocks is 3/2, then by setting up this relatively simple equation, 3/2 times what would give me 9 blocks, I can find out that it takes 6 blocks to equal 1. And that's the same thing we got before. And this might make sense to you then when you look at it and say, oh, all right, if this is 1, then this would, putting those together, would be 1.5. Because 6 blocks is 1, so 9 blocks would be 1.5. At the end of it, it can make sense. Your problem-solving process here you can do it totally visually, like the first thing that I set up. Second thing you can do is say, all right, well, there's 9 blocks total. You're telling me that that's 1.5. Well, 1.5 is the same as 3/2. So 3/2 times x has to equal 9. This x will be the number of blocks that 1 is. When I solve that, And I could do it by multiplying by 2/3. We could solve it by doing what Laura suggested. Let me try to find some space on here to squeeze that in. When we had 3/2 times x is equal to 9, Laura's suggestion was multiply by 2. Okay, if I multiply by 2 on both sides, now these 2's cancel, and I have 3x equals 18. And then I can divide both sides by 3 and wind up with x equals 6. You might like that better than this reciprocal stuff. Laura's way might appeal to you. It's perfectly fine to do it that way. Nothing wrong with that at all. But basically, we found out that it takes 6 blocks to be 1. Let me know if you have any questions on that. I do think it's a little bit challenging. Okay. I want to have you try one. In the diagram below, if that's 1 3/4, show 1. So if that's 1 3/4, what would 1 be? How many blocks would there be in 1? So that's what my poll question to you is going to be. How many blocks are in 1? You might be able to do this one visually, or you might need the idea that 1 3/4 would be 7/4. And I'll go ahead and throw that your way. I think this one might be easier than the last one to do visually. You may or may not agree with that. I can't really speak for the visually. You're probably better at seeing that than I am. So let's go another 25 seconds. If you need more time, let me know. If you get an answer that's not there, you can pick the one closest to yours. But it's, how many blocks does it take to make 1 if that is a picture of 1 3/4? Okay, let's see how we did on this one. Oh, very good. Strong agreement, although we are spread around on all the answers on this one. So let's talk through this and make sure that we can get to the right place. One of the things that those of your visual might see here, well, if I make this 1, then this is 3/4 of 1. So that's it. It's just those 4 blocks at the front. That's 1. And then this is 3/4 of the next one. So that's one way to go. Some of you might like the equation method, and you'd say there's 1, 2, 3, 4, 5, 6, 7 blocks. So 7 blocks is equal to 1 3/4. 1 3/4. Okay, so that would be 4/4 plus 3/4 would be 7/4. So 7 blocks is 7/4 of whatever 1 is. And that's what I'm calling x. Now I need to solve this. And I don't know, I kind of like Laura's way. I'm going to do it this time. We're going to multiply by 4 on both sides and have 28 equals 7x. And now I'm going to divide both sides by 7. And those cancel. And I get 4 is equal to x. And so 4 boxes is 1. So that's what 1 would look like, is those 4 boxes. Let me know if you have questions on that, if you have any trouble on that. Okay, very good. I do think those can be a little challenging, so be patient with yourself when you work on those in the homework problems. Okay. I mentioned the area model was going to sort of be our go-to, and we're going to do some problem solving with the area model here. 4 ounces of medicine is in a bottle, and a dose is 1 1/3 ounces. How many doses are in the bottle? Your first thought here might be, well, seems to me like you just divide. You're not wrong, but maybe the kids you're working with don't know how to divide fractions yet, or maybe they haven't worked with mixed numbers really very much yet. So instead, we can do this with the area model before they ever learn those things. I have 4 ounces of medicine. So I'm going to go ahead and draw that using the area model. There's my 4 ounces of medicine. Each one of those represents 1 ounce. I know that a dose is 1 1/3. So what I'm going to do is I'm going to cut these into thirds. And now I'm just going to count up how many doses I have. So let's see. A dose is 1 1/3 ounces. So I need a whole ounce plus a third more. So that'll be my first dose is a whole ounce plus a third more. Let me know if what I'm doing doesn't make sense or you're not sure of why I'm doing it. There's a couple different ways you could go from here on how you want to count these. I tend to just keep going left to right, but I've seen students do it a different way that I'll show you in just a minute. Okay, so the next dose is 1 1/3. So my second dose is going to be 1 whole ounce plus another third. And then my third dose is going to be 1 whole ounce plus another third. And that's it. So 4 ounces of medicine's in a bottle. A dose is 1 1/3 ounces. How many doses are there in this bottle? There are 3 doses in the bottle. I didn't have to know how to divide fractions at all. I used the area model to solve this question. I mentioned that for this particular question, you may do your labeling a little different. You might do that for your first dose, and then for your second dose, you might say, well, it's a whole ounce plus another third. And then for your next dose, it's a whole ounce plus another third. Then you still wind up with three total doses in your bottle. That works fine too. You don't have to do it left to right. I tend to, but you don't have to. Let me know if you have questions on this before I have you try one that's similar. Okay. 5 ounces of medicine is in a bottle, and a dose is 1 1/4 ounces. How many doses are in the bottle? Try this using the area model. I'm going to set up a poll for you, and then we'll talk about it in a few minutes. And this is the area model, allowing us to solve a problem like this when we don't know anything about how to divide fractions. Since we're doing the area model, we're doing this with the picture. Um, I'll probably do it with circles, but you can use rectangles if you want to. The reason I'll use circles is because the next example we look at, I'm definitely going to use rectangles, so I want to make sure I do a little bit of each. We'll go another 30 seconds, and then we'll talk about it. All right, let's see how we did. Okay, really strong agreement here. We'll go ahead and talk through it, and you let me know if you have any questions. Um, the idea here is to say, okay, I'm supposed to figure out how many doses there are in these 5 ounces of medicine. I'm going to go ahead and make my 5 ounces of medicine be these circles right here. And then because a dose is 1 1/4 ounces, I'm going to cut my circles into fourths. Like I said, it's perfectly fine if you wanted to use rectangles or squares for this. Same idea. And now I need to count it up. So let's see, a dose is 1 1/4. So my first dose is going to be a whole ounce plus a fourth more. My second dose will be a whole ounce plus another fourth. My third will be a whole ounce plus another fourth. And then my fourth dose will be a whole ounce plus another fourth. And we end up with 4 doses in the bottle. And we effectively just did 5 divided by 1 1/4 without understanding mixed numbers or how to divide fractions. Let me know if you have any questions on that. Okay. This one reads like it's harder because it is. There was a grove of trees in the forest. Fungus infected 1/3 of them, damaging the wood. Of the remaining trees, loggers came in and cut down 2/5 of those. 48 trees were left over. How many trees were there at the start? Now, just reading this seems like a really challenging question. And trying to work backwards, starting with 48 and using the fractions and maybe the reciprocals of those, you might be able to get there. But honestly, I think the area model gives us a beautiful way of solving this question. So there was a grove of trees in the forest. Okay, well, here we go. I'm going to make my grove of trees. There it is. There's my grove of trees. Fungus infected 1/3 of them, damaging the wood. So I want to identify 1/3 of these. So I'm going to go ahead and cut it into thirds. And what I know at this point is fungus damaged those. So I'm using the area model to show this 1/3 as a part of my problem solving process. Earlier today, we just said, what would 1/3 look like if we use the area model? Now we're going to do that, but use it as part of a problem solving process. And if I do something here that doesn't make sense or you're not sure where it came from, absolutely ask me. I think these problems are super cool and fun, but I want to make sure that you get the process. Fungus infected 1/3, damaging the wood. So there's the ones that are damaged. Of the remaining trees. So now we're just talking about these over here. Those ones that didn't get damaged by the fungus. Loggers came in and cut down 2/5 of those. So 2/5 of the remaining got cut down. So we want to cut those into fifths. what we're going to do is we're just going to cut this whole rectangle into fifths. So it doesn't have to be perfect, but you want it to represent it. So let's make sure here I have 1, 2, 3, 4, 5. Yes, I've cut it into fifths. I cut it the other direction because I didn't want to try to cut it in the same direction as my thirds. Now I wanted to cut it into fifths. And what those loggers did was, now that I have these fifths, the loggers cut down 2/5 of what remained. So what the loggers cut down is there, that 2/5 right there. Again, let me know if I do something that doesn't make sense. So I sectioned this off into thirds, and I shaded one of those thirds because that's the fungus infected. Then I cut it in fifths the other way. That's why I used a rectangle here, so I could cut it both directions. That's hard to do with a circle. And the loggers cut down 2/5, so I had to identify those 2/5. And now I have 48 trees remaining. And the question says, how many trees were there at the beginning? What I know at this point is that I have 48 trees all together in these 6 boxes. And I can divide them and say 48 divided by 6. That means there are 8 trees in each box. So there's 8 trees in each box. And I can take that one step further. If there's 8 trees in this box, and there's 8 trees in this, there's 8 trees in every box in this whole thing. Every box is the same size because that's how I cut it. And so we have, let's see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 boxes altogether. So 15 boxes times 8 in each box. That'll give me the total number of trees that were in the forest at the beginning. And that's 120. It's a pretty complicated question. We're able to solve it without using any sort of algorithm or equation at all. We just use the area model and a picture to solve it. Let me know if you have questions on this before I have you try one that's similar. Very good. Okay, here goes. There was a bowl of jelly beans on the table. Larry ate half of them. Then Mo ate 1/4 of the remaining jelly beans. And then Curly came along and ate 2/3 of those. After all that, 4 jelly beans were left. How many jelly beans were there at the start? My advice is to use a rectangle and cut it up the way that this problem asks you to. I'll make a poll for this and we'll talk about it in a couple minutes. I do think these can be really fun. I also think it takes a little bit of practice to get the hang of it. This isn't the kind of thing that takes a ton of practice to get the hang of it. I think a little bit of practice and then you get the hang of it and they're really fun to do. And I hope that's true for everybody. Similar to that last one, this is one that you could try to do by starting with 4 and building back up by using the fractions that are in the problem, but I think the area model is a much nicer way to go. It's a problem-solving technique that we uh, I never really see typically, and it's pretty terrific. Let's go another 30 seconds on this, and then we'll talk about it together. If you need more time, let me know. If you get an answer that's not there, pick the one closest to yours. I saw a couple answers come in there. That's why I haven't cut it off yet. So this one might have just taken a little extra time, and that's okay. It's probably a very new idea. All right, let's see how we did. Uh, okay, strong agreement. Not unanimous, but definitely strong agreement, and only one alternate answer. That's good news. Okay, so let's take a look at this one. The idea here is there's a bowl of jelly beans on the table. Larry ate half, Mo ate 1/4 of what remained, and Curly came along and ate 2/3 of those, and there were 4 left. How many jelly beans at the start? So what I'm going to do is I'm going to start with my bowl of jelly beans, but I'm going to draw it like a rectangle. And then Larry ate half of them. So the first thing that happened is I'm going to cut this in half, and Larry ate those. You could have cut it vertically. That's fine. No problem. Um, okay, then Larry ate half, so we took care of that. Now Mo ate 1/4 of what was left. So what I have left down there, I need to cut into fourths. And Mo ate 1/4 of those. Okay, so that's Mo. Okay, and now Curly ate 2/3 of what was left at this point. So Curly came along and ate 2/3 of what was left. So I have 3 pieces. So if Curly ate 2/3 of those, then Curly ate 2 of the boxes, and 4 jelly beans were left. And so what that means is after all is said and done, I have 4 jelly beans in this box. A little bit of danger here. We don't want to say, well, there's 1, 2, 3, 4, 5 boxes and 4 jelly beans, so it's 20. What we want to say here is, well, wait a minute. There's 4 in this box. How many of those size boxes would it take to make the whole thing? And it would take 1, 2, 3, 4, 5, 6, 7, 8 of that size box. And so 4 jelly beans in one box times 8 boxes that are the same size, there were 32 jelly beans when we started. And you can double check this if you want to when you're done. There were 32. Well, Larry ate half. So Larry ate 16, and that left 16 still in the jar. And then Mo ate 1/4 of those. So I guess Mo ate 4, and that left 12 in the jar. Curly came and ate 2/3 of those, 2/3 of 12. Yeah, we did that one earlier with the 8 out of 12 was 2/3 of a foot. So I guess that means Curly ate 8. And sure enough, that leaves 4 in the jar. So I feel great about my answer of 32. Let me know if you have any questions about that one. It went really well. You may have drawn it slightly differently, but a lot of people got to the right answer there, which is terrific.